Hello and welcome everyone. Today I'm going to talk about the crypto and economic incentivization of the Crosschain Protocol Stack. And I don't know, if you pause the video, you can read all about me. So I'm going to talk about how the Crosschain Protocol Stack and GPACT interrelate and talk about the economic models you could use with the Crosschain Protocol Stack. So the Crosschain Protocol Stack is an idea where you've got applications that have business logic across chains. You have a function call layer, which allows those applications to call functions on different blockchains. And then you have a messaging layer, which allows you to trust that events have occurred on remote blockchains. And so GPACT is a protocol that operates at that function call layer. And so talking through the capabilities of GPACT. So one is that it provides atomicity. So either all the updates on chains are committed or they're discarded. And so, for instance, you could imagine this sort of thing where you, on a source chain, you call to a destination chain and you could revert if something, some condition's not met. And so in addition to reverting, you could maybe have some sort of software failure in the relayer mechanism, or maybe the relayer can't submit the transaction because they don't have permission, they can't pay for gas or something like that. And so, what happens if that happens? And so you're going to have something's happened on the source side, but then on the target side, it didn't occur, and that's going to leave you in inconsistent state, which say if you were doing a value transfer, such as the example at the bottom there, then Alice would escrow 2 ETH on the source chain, but then get nothing on the target chain. And that would be a bit of a mess. As well, the technology allows for multi-chain. So rather than just being between 2 chains, it can allow you to spread business logic across multiple chains. It allows you to have values returned by function calls as well. So you can have some logic, business logic that calls a blockchain and then gets a return result as part of execution. It also allows for conditional logic. So you could be calling one thing or another thing, and you don't, it can depend on the parameter values and your business logic as to what actually gets called. You can also do application authentication. So essentially, in a similar way to how you had message sender equals authorized, where you need to know, well, is the source like from the correct blockchain that I'm happy with, and contract. And so you're going to have an allow list that might cover those. As well, the technology allows for a similar programming model to what people are used to with Solidity in the EVM. And so you can have composable programming where you're going to bring together components from different chains, different contracts, and you can execute synchronously with it from the perspective of the actual Solidity code. So you can go and call a function and get a result immediately. So you don't have to worry about asynchronous execution. So how does GPACT work? So there's a technical paper. There's actually IEEE paper, peer-reviewed papers as well, but that's an open access version there. And there's also a GitHub repo. And so the idea is you have an arbitrary call execution tree that you create, and you have the entry point function calls in contracts on blockchains with certain parameter values. And you say, I'm going to execute that. And so you publish what you plan to execute. And in the V2 of GPACT, there's a privacy preserving methodology, but we're not going to go into that. So you commit to what you're going to execute. And then you execute segments, which are part of the execution. So at the tips of the tree and then working up to the root of the tree. And so you say, well, this piece of code executed on this chain and it returned this value. And it executed successfully and it locked these contracts. And that's all going to go up to the root. And then the root's going to say, hey, everything's executed okay. And I've executed okay as well. So we should commit all the changes on all blockchains. And then it'll say emit an event, and then these signaling transactions are used to commit the changes on the other blockchains. Within a single chain, how it works is you've got a cross-chain control contract and you have start, segment, root, and signaling function calls, and they call out to business logic contracts that you've got once information has been verified. And so it's up to this messaging layer to verify that an event that has happened on a remote blockchain really did happen. And then once you're executed the business logic, so based on that call execution tree you committed to, you then are going to indicate that, hey, this storage location's been locked. And so, later on, you're going to need to unlock this. And as well, you can do cross-chain function calls. And in that situation, you're saying, look, I'm expecting to execute this function in this contract on that blockchain with these parameters. And if it matches, then it's all good. And if it doesn't, then the overall transaction is going to fail. The messaging layer for this and the function call layer are in the midst of being standardized. And if you have a look at that link there, you'll see the draft standards. And in those draft standards, you'll see things like this, where you've got that verifier interface defined. And this is saying between the function call layer and the messaging layer, here's an event that has occurred on a remote blockchain. Can you verify that for me and say, is it valid or not? And the each remote blockchain might have a different verifier, and it allows you to trust that information is correct. Importantly, the messaging layers can only act on finalized information. So if you've got information that could possibly change, then you can't act on it. And as well, at the function call layer, here's an example of a function call we've got where you're essentially calling a function that's going to return a uint 256. And you specify the blockchain and the contract you're going to execute and the function selector. And if there were any parameters, you'd specify them. And you can get the return value back immediately. So the architecture of the system is likely to be, multiple blockchains, and you're going to have a test or relayers for each chain. And you're going to have some infrastructure contracts, so the GPAC contract, so verifier contracts for each remote chain. And then you're going to have your application. And then you're going to have an SDK, which is sitting inside an application, which helps orchestrate the various transactions. So you could imagine you could have one application and it could deploy a GPAC contract and it could run its own verifiers and it could run its own nodes as well. But then if you had two applications, then you could imagine you could do that twice. But then say if we have 1,000 applications, then we're going to have 1,000 sets of relays. And I'm pretty sure that not all of those companies that are operating those whole stacks are going to be capable of operating them securely. And so another way of doing it would be that the companies could deploy their own GPACT contracts and use shared verifiers, and so pay another company to have a verifier that they use. Or you could imagine the company that's operating the testers, the relayers, it could deploy its own function call contract and say, hey, applications, if you want to use my system, you just use my function call contract that I've deployed. So looking at the messaging layer, so there are a few different approaches for messaging, and one of them is threshold signing. So that's where you have M of N relayers, and they agree on whether something has happened on a source chain or not. And if they do, then it's going to verify on that target chain. And so you could be having the situation where you're signing an individual event or message, or it could be that a Merkle root, say a block header is signed. The signing could be done each node separately, or you could have some sort of cooperative multi-signing where each node signs and they send their signatures to each other, and then only one node maybe submits the multiple signatures to the destination. You could also have MPC, multi-party computation signing, where the nodes cooperate together and they create a single threshold signature. And in that case, you're not going to be sure who's signed. You're just going to know at least a threshold number of the parties have signed. And so sometimes you can have slashing in these systems, and that's where a node's going to lose their stake if they do something bad. So they sign something that's incorrect, or yeah. And so the relayers you could have a system where the relayer transfers assigned messages. You could have a situation where a relayer transfers assigned Merkle root, and then the user relays the messages. Or you could have it that the attester, you generate signed messages, and then the user gets them from some sort of web service, and then the user relays the messages. So they've each got their advantages and disadvantages. And so I'm not going to delve into the security and other thoughts on the actual mechanisms, but just trying to think about threshold signing and incentivization. So one way would be that you could pay a monthly fee. And so those verifiers could say, well, I'm going to watch your contract because you're paying me a monthly fee. And so a good thing about this is there's no gas that needs to be paid each time you're relaying a block header or an event. And so it's simple as well. But the thing is, say if you have M of N, how do you ensure that all N of the parties are participating? Like you could imagine M of the parties always return really quickly and with their signed information, but then you could have, like, say, some of the parties that are essentially offline, and are they still going to get part of the share? And maybe that's within the messaging protocol an incentivization issue that needs to be thought through. So that can be a bit tricky. Another way you could do it is you could have some sort of on-chain payment. So this is going to be good because it's going to be direct attribution of each of the signers. And so you could imagine on the verification side, when you go to verify a message, you could say, all right, I'm verifying this message and I'm going to pay each validator that's signed, or each relayer that signs the message. And so that's, however, going to cost you money to actually pay the validators on that target chain, because it costs 20,000 gas to update a storage location. So say if you had 5 relayers, then that's 100,000 gas to update their balances, and then 20,000 gas to decrease the balance of whoever's paying for it. And so another thought is, though, if you had, say, an M of N system where you're relaying to a target chain, and each is individually transferring their messages, then only the fastest of those M of N are going to be getting paid. And so the other N, other parties that aren't as fast, maybe have higher network latency or something, they're not going to get paid. So are they incentivized to participate in the system? And for the MPC system, you're not going to know who has signed. So there's only going to be one signature. So you're still going to be paying, you're going to pay per message or Merkle route that's been transferred. And then you're going to, the messaging layer company or consortium are going to have to work out a fair way of distributing the payments. Another way could be micropayments. And so, so in this situation, for each record that gets signed, you get paid a micropayment. And, so you can sort of directly attribute who's signed, because you give the micropayment for the signature. And it's off-chain, so there shouldn't be many fees, but, as far as you're not going to be paying gas costs. But on the other hand, though, but it's a bit like a payment channel. You are going to have a settlement or setup and settlement fee and that's going to take a while to do it. And as well, it's going to be more complicated because you're essentially setting up your own payment channel system. Another thought on is with threshold signing is about staking and bribing. So an attacker could bribe M of the N relayers and then get them to sign invalid information. And this is probably the more likely scenario given recent events, an attacker could steal the private keys. And that's been done recently. So if, if the sign of information can be cryptographically proven to be fraudulent, then you only need one watcher. And that watcher doesn't even need to be a relay or a tester to prove the fraudulent behavior. However, they could be front run. So even if you prove some fraudulent behavior, if you might have an MEV attack where some miner says, hey, I could get some reward, and then they might put it in. And so if M is less than half though of N, which, is a bit of a tricky situation, but, possible, then you could imagine that M parties could sign and then M other parties could slash them. But then maybe the party slashing is the fraudulent ones rather than the other parties. So I think M being greater than half of N is probably required. Otherwise, it's going to get messy. You can also, so as well as threshold, you can have optimistic approaches. And so in this scenario, you have N relayers, and one of the N says that something's happened. And then there's a delay period before people should act on that on the target side. So it's almost like another type of finalization almost. And the idea is you've got watchers that are watching to make sure you've got have got good behavior. And there are some options on how you even do this. And so one is that you have cryptographic proof of bad behavior. So you can definitively say that happened. And in that case, you can have any can be a watcher and can cryptographically prove. Or you could have M of N validators or attesters vote, but then it starts to feel a little bit like a popularity contest. And I do worry about voting as opposed to cryptographically proving. And you've got also, so are those watchers permissioned or permissionless? And so permissionless is better because then you've got more people that you'd have to bribe. And as far as the proof is concerned, you could have an open proof where, a miner who's going to do MEV could look at it and go, hey, I could do that proof. I can just copy the proof information and submit it myself and get the reward. Or you could have a commit reveal system where you commit to that there is an attack and you know what it is and here's the information. And part of that information could be, and I'm the one who found it. And then you could reveal. However, you can imagine the attacker, if they were in the position to be able to MEV, they could be watching you putting in your proof, and they could MEV you. So the attacker could MEV you when you're proving that they've attacked, which would be bad because then they're not having a cost of attack. So some other, so there are some other financial things to think about as well that I haven't covered. So I think I've actually went through a few of these, but one of them is, so so one of the N attesters submits a transaction on the, so typically how they work is you submit a transaction on your source chain to create an incremental Merkle tree, and then you have a relayer relay that Merkle root. And so who gets to choose who does these transactions? Because the actual transactions cost money. And if you have multiple parties wanting to do the transactions, then you've got the issue of different parties competing. And so some people are going to be spending money on transactions and aren't going to go through. And I think the rest of them are things that I went through on the previous slide. Another option for the messaging layer is to have a light client. And so you're essentially emulating the consensus protocol of the source chain. And so depending on the consensus protocol of the source chain, it could be simple, complicated, incredibly complicated, or just ridiculously complicated. And so, and you could do it on-chain or off-chain. And so if you're doing it on-chain, you're trying to do all the calculations. But another alternative would be you could have a zero-knowledge proof system that proved that, this consensus worked, and so that you could leverage that zero knowledge proof. Yeah, and so it's complicated though. So how do you incentivize this behavior, for people to do it? So you could pay the relayers per month or per message. And so, it's great because it's trustless, assuming you trust that source chain. But, you're probably going to have to transfer each and every block, even if the system isn't being used. And that could end up being really costly. Or you could have massive latency and only, say, transfer like a whole lot of blocks all at once. So yeah, it depends on the scenario, but you are going to be probably paying for empty blocks, which is costly. Okay, so I've talked about incentivization at the messaging layer. What about the function call layer? So so one of the ideas you could do is you could have the, how I said there was a start function, you could have that as a payable function. And so when you call the start function, you transfer some ether across. And so you pay the value. And, the advantage of this is that, you're just paying at the start and you're paying once. But then, I guess you only need to have the ability to pay for ether on that root chain and not on all these other chains, which could be good because maybe the value you need is high. However, say if the different chains are operated by different people, then you're paying on that root blockchain, but not on the chains that the segments are executing on, and so that doesn't seem necessarily very fair. So you're not paying where you're actually using, and yeah, so you'd have to work out how you're going to distribute funds to the other chains. And for rollups, it's not going to work because they don't have the concept of ether. You've only got ERC20 tokens. You could have an ERC20. And so you could have some token, and the idea is you call start, and then start calls out to some ERC20 token and does a transfer from message sender to the GPAC contract. So the message sender would have had to have authorized that earlier on by an approve. And, so you can imagine that, this is good because it's going to work on those roll-ups now because you're using an ERC20. But, the user has to have that ERC20 token and on the root chain. Again, it's got that problem that you're not paying on all the chains you're operating on, and you are going to have to be paying 40,000 gas because you're going to be increasing the balance of the operator and decreasing it of the user. So that's 40,000 gas extra that you're automatically going to pay. Another idea could be that you do ether payments for each of these start, segment, and root function calls. And that's a possibility too. And so you could have them all payable and you could pay there. And so you're paying, so you would be then paying for the attesters and relayers that are doing the work, because each attester and relayer is related to a chain, and so you're going to pay for that work to be done. So the problem, of course, is that net users now going to have value on all the chains, and I guess they're going to have to pay for gas anyway, but this might be more money, so they might not want to be doing that. It might also be difficult for them to estimate fees ahead of time, and it won't work with rollups because it's not an ERC20. If you did have use an ERC20 though, and for all of the different function calls, then the relayers, the testers are going to be paid for all their work. But the user is going to have funds, well, in particular those tokens, on all the different chains. And again, the user might have difficulty estimating the overall fees, but and the overall transactions are going to be 40,000 gas more per chain per segment. And yeah, so that's going to be potentially quite significant. So what about at the application layer? So the application layer, it really depends on what the application is, but I'm just going to walk through a thought experiment. So Alice wants to do an ERC20 transfer to a target chain. And she says, but by the way, I can't pay I don't have any gas or ability to pay for gas on the target chain. So Bob, can you do the transfer for me and I'll incentivize you? So let's assume that the incentivization for Bob to do the transfer is all cool. So she does an ERC20 approve on the source chain. Bob submits start saying, I'm going to execute this call execution tree. Bob does segment, and which provisionally transfers the value from him to Alice on the target chain. He then does the route to finalize the transfer from Alice to himself on the source chain. And then he does the signaling to finalize that transfer on the target chain. And so now Alice has got her money. Great. However, Bob is not incentivized to do that last function call, that last transaction. Why should he submit that signaling transaction? Sure, he won't have the money, but nor will Alice. And, it would damage his reputation, but still it's, not a biggie for him maybe. So an alternative way of doing things would be Alice can again request Bob and does the ERC20 approve. This time Bob does the start call on the target chain. And then he does the segment to provisionally transfer from Alice to himself. And he does the route, which does the provisional, then finalize to transfer from himself to Alice. So Alice has now got her money. And then he does the signaling, and then that gives him the money. And by it being him who gets his money last, it incentivizes him to do it. And so it's an interesting one to think about, that if there's adversarial commerce going on, then you do need to think about who is incentivized to do what at the application layer as well as the lower layers. So some final thoughts. So the GPACT contract trust relationship with the various relayers and attesters is really important. And because you want those relays and attesters to sign your messages or transfer Merkle routes across. And so you're going to need to have a way of incentivizing them. And so they might do things to try and prevent you from using their technology if you're just freeloading. Or you could run your own relayers, but running relayers is a complicated thing, and maybe you're best off leaving that to other people who have experience doing it. I guess that's the thing. Running those relayers is complicated, and so operating them should be valuable. So maybe you might have to pay for them. And if you've got any questions, you can fire away. So for those watching this on YouTube, please just put comments in to the against the video. Thank you. Bye-bye.